Yo, what's up, what's up, what's up? Welcome back. Today we're working on my image to text neural network, where text, I don't mean like a label for an image, but I actually mean like a text representation of an image. So where we're kind of at in the project right now is we have like an image that we've looked at. We have like generated labels for it that look kind of like this, right? So we go from left to right, and if we like zoom in, we can see that like, oh, these are actually UTF-8 characters that we've loaded from like a specific font. And we've trained a neural network to predict those. And if we look at or predict the same answer as what our labels do, and if we look at that guy, like at like a zoomed out level, it looks pretty similar. When we zoom in, we can start to find some like inconsistencies, probably, but overall, it's looking like pretty good. Right? If we look over here, let's see. Let's like zoom in on like this area here on the very bottom. Right? Like it looks like a little bit different, but like the overall shape when we zoom out looks pretty good in both like the trained version and the labeled version. The difference is that one of these, when we did them last stream, was on the order, or sorry, maybe when we compared performance a couple streams ago, was on the order of like a couple hundred times faster, or maybe even more. I think it went down from like 15 seconds to label versus like more like 0.1 or 10 milliseconds to run the neural network, if I remember correctly. So the idea is we train a neural network, and that should give us a similarly like good result, but for much cheaper compute. Right? The idea is that we tank compute up front to when we train the neural network to create something that will be reasonable, and then we get like the benefits later. And you might ask like, well, do we really need that? Like, how expensive can this really be? And so, like, let's just imagine, you know, we have like a 5x5 image. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And let's say that we're like trying to convert this into like a single character, right? So we want like, you know, we draw like a little number 1 here, and we want this to get mapped to like the number 1 in text, right? And so say that these are black and white. Well, that's like 2 options for 25 pixels, so 2 to the power of 25 options, which is a lot. And probably it's not black and white. It's probably like, at the very least, you probably want like at least like 8 values or something. So you have like 8 to the power of 25. Those are your like possible options. So you can't just like pre-compute a lookup. Okay, so you can compare like your sample against every single character. And that's what we do during label generation. And it turns out that that's like quite expensive, because there's like 1,500 characters in our font, and we want to render them at like a resolution where they're like reasonable. So this ends up being like maybe like 20 by 30 pixels or something. And then we had to expand it even more to get like to like tune our results to make them the way we wanted. So all of that to say that we're doing like a lot of comparisons. It just turns out that's just expensive. So that's why we're doing what we're doing. That's where we're at. And so what I wanted to work on today was, right now we've like trained on this one image and it looks like decent, but we haven't ever like got to the point where we've trained on like a full data set of varied images, and we haven't tried like transferring this from one image to another. Like we haven't tried running this on like we haven't seen like how well does this generalize, I guess. And so there's a good chance that our current network is like so fucking stupid that it won't generalize at all. But we want a way to like prove that, I guess. So first we want to like get our thing training on another data set, and then we want to like see how it's doing. We don't really have any way to like see how it's doing right now. The only thing that we have right now is just like one image, and we can run on that one image. But like, what does it like mean to be successful? Not very clear. So, we're gonna try to train that. We're gonna try to find some sort of metric that we like for correctness, and then we can, if we get to that, we can maybe try to like try improving that metric in some way and see how we feel about it. But before we get to any of that, I did want to go over the improvements that we made for performance to get here. So let's hammer those out real quick. So let's see. I guess probably what makes sense here is I've like made a little branch here where I've logged like the speed with which we can like generate labels on the CPU and GPU. So we have like this visualization script, and instead of like doing the visualization, I'll just run this with this one sample image we're looking at. And instead of like serving this web UI that we're looking at right now, we're just going to log how long it took to generate the labels, essentially. And if I remember correctly, the starting point was around like 15 seconds, 18 seconds on the CPU. I don't know if like me streaming is going to affect that. So we'll see approximately how long this takes. And of course, with all benchmarking, like we're kind of, our benchmarks aren't going to be like super, super accurate if we only run it with things like once per thing. But okay, 21 seconds, approximately, right? There's some variance there, but let's just say approximately 21 seconds. At the end of the improvements, it should be closer to like 1 or 2 seconds on the CPU, I think. Let's just see. Yeah, 2.3. So we got like a 10x speed up on label generation, which is like pretty good. And I just wanted to show like, well, what were those improvements? So let's maybe start here, and we'll just kind of walk through them. Oopsies. Here to demo. Okay, so the first one was we were using, how do we say this? We were going through every single sample in our image. So like the labeling process as a whole. We like have our picture over here. We have like the sun and the mountain, right? And like maybe like these hills on the side and the water. What we do is we basically like, we take a chunk, take another chunk, and we just like split this guy into chunks that are approximately like some width of the image wide. We're using 12 pixels here. We render a character for each, we render every single character for each of those samples, and then we do like a direct one-to-one comparison of them. So that means we have to do like a nested for, right? We need for each sample, compare for each character, do a comparison. And the way we were doing that before is we just didn't understand like some of like the like PyTorch rules on this stuff. But we were basically saying that if we wanted to do all of those comparisons at once, we needed like arrays that had the correct shape. So we needed like we had like num samples by height by width. It was like a 3-dimensional array, so like basically a collection of 2D pictures. And then we had number of characters by height by width. And we needed to end up with like comparisons that were of the order of like number of samples by number of characters by height by width is like our sample space, or like comparison space, I guess. And so what we did before was we were basically saying like, okay, so for this guy, we kind of need to be able to do a n by c operation here. And so the way we did it before was we just repeated this first thing like 1,000 times for each character. And it turns out you just don't have to do that. You can just ask the PyTorch code to do that for you. So that's kind of what we did here, is we just kind of like removed this like repeat that we were doing before. Pretty straightforward fix, but that gained us around like 30% improvement, which is pretty sick. Then what else do we do? We have like this like blurred version of all of our characters, because the idea is that like if we take like a character that looks like an A or something, or like an A, is this what they look like when you draw them out? And you take like, you try to like compare that to a sample. If you have like something that's like right here and it like doesn't match perfectly with the A, then it will be counted as like a really bad match. And so what we do is we kind of like blur the glyph a little bit before we compare, basically to say like, hey, you have like an area of effect, and if you're close by, that's like good enough. And we were doing that like every time we did a label before, and it turns out that you can just pre-cache that, easy peasy. So that's like another like 10% maybe. Lower glyph cache res diff, right? So it turns out that we had to like do that blur at like a pretty high resolution because we need the effect of that blur to be kind of low. And so if you have like, if you're trying to blur, like if you have like, if your thing was like 9 pixels, right? And you're trying to like blur this pixel with this pixel, you basically have no choice but to like affect a 33% of the image, right? right? Because if you're like blurring these guys together, you are just going to affect that. So what we did was we upsampled more to blur, but it turns out that after you apply the blur, then you can downsample again, and arguably there's something wrong there, right? You should be able to, like, if you only have 10 pixels, you should only need to affect those 10 pixels. But we haven't really found the right combination there. So we upsample to blur, then we downsample back into our comparison, and that ends up, if we divide our like width and height by 2, that ends up being like a quarter of the work that you have to do. So we got like around like another like 75% speed up on CPU, 40% on GPU. And then here's like the one that really unlocked a lot for us is the thought was, you have to do a certain amount of comparisons, right? If you're looking at a sample, you have to look at all the pixels. And so like if you're doing this many comparisons, how can you like get the work down, right? Because like the way to get faster is just to do less things. And it turns out that you can like think of doing less things in like multiple dimensions, right? There's one that is like number of pixels. How many pixels am I comparing? I want to do less pixels, right? That's what we did by halving the width and height of our samples. But it turns out that you can also think of it as, well, how many instructions do I need to issue to do those comparisons? And how much memory bandwidth am I using to do those instructions? And if you just pack your pixels into like less bits, then your comparisons can do less, or like they can go faster essentially, right? Because if you have like, if you're using like SIMD, which is basically like, I'm going to pack a bunch of operations into one like big register. So you have like a 128-bit register. You could think of that as, well, if your numbers are like 64 bits wide, you can do 2 operations at once. And if they're 32 bits wide, you can do 4 operations at once. If they're 16 bits wide, you can do 8. And if they're 8 bits wide, you can do 32. No. 2, 4, 8, 16? 16? Yeah. So you can do like more if your pixels are smaller. So we basically like took all of our computations there, and we moved our images into like 8-bit space. Instead of floating point numbers, we just put them into like 8-bit numbers. And then we just tried to like make sure to limit everything that we could to like the lowest amount of bits possible. So before, like if we did like this subtraction, that would upcast to like, or that would like, sorry, not the subtraction, the sum that we do somewhere, we like add up we diff all the numbers and we add up the differences. This would automatically convert into like a uint64, or this might like automatically convert into like uint32. Or like this sum might require like an int32 to fit all the things. So we do like some tricks here where we basically say like, we're going to like manually set our types, make sure that like we're doing 8-bit subtractions in int16 space. Then we do like a right shift to basically say like lose some precision. But by losing that precision, we can then fit the sum of like all of our values, all of our differences into like a 16-bit number, which we wouldn't have been able to do. So the trick is just like, what can we do to try to like use less memory, essentially? And that gained us like a pretty good amount of speed on the CPU, 40% on the CPU, low improvement on the GPU. However, this unlocks another improvement on the GPU that had like a major effect, like another 40%, which is basically that before we were using so much memory in our scoring that we had to batch up our scoring section into like multiple chunks, like do like 100 at a time, label all these 100 characters at a time. And we saved so much memory that we could just do that in like one shot now. We could like just do our whole batch at once. And it turns out that doing more on the GPU at one time is good. Who could have seen that coming? Because it's like massively parallel. So that's like gives us like another 40% speed up on the GPU. So after all that, we went from the point where it was basically essentially untrainable to where we should be able to go to this branch and we should be able to train something. Still running on the GPU. And here you can see it's like, it's moving. It's not moving super fast. Before we were doing like 1,000 iterations every few seconds. But it's at least like at the point where it's making progress at like a rate that I feel like is reasonable to go into on stream. So let's actually go into the training script and we'll do what we were doing before, and we were training on a single image. So I'm just gonna like back out some changes here. It was this guy, and this guy's what I have to change, I think. So now we're gonna say, I'm gonna train only on that image we were showing earlier, this mountain range. And we can kind of see how long does it take before we start to see like a reasonable output from the network. So here we've gone through about 50 steps. It writes down its like current state every 200 or so. So if we wait maybe another like 15 seconds, we should be able to at least see a result. Maybe it's not very good, but we will at least see something. Almost there. 200. So at 200, we start to see something that's like resembling the right answer. Clearly it's not very good yet, but it's got like kind of like some of the major features, right? Like it's got this part of the sky, it's got like this like piece of sunlight is like starting to show up. It's like not very good at like distinguishing some of these like more detailed features in the mountain at this point. But maybe we'll see when it gets to step 400 that it gets a little better here. Let's give it a sec. Let's see. Learning rate might be a little too high there. We actually see a big jump. But we're at like maybe a loss 0.5 now. And if we look at what we see here, this guy's starting to look like pretty decent, I think. Like, again, not perfect, but the mountain's starting to have like some texture to it. The land in the bottom left is starting to look pretty decent compared to the original. Like here, I would probably say it's like starting to look almost good enough. Maybe we'll give it one more, give it till 600 just to give it like one more chance. But like, yeah, that's like, how long have we been training for? Like 2 minutes, and it's already looking like that's pretty damn good, right? That's good enough, I think. So that's kind of like where we're at if we train at a single image. And so it'd be kind of interesting to see, well, if we upgrade our training process, which we've started working on, and start trying to train on like a more varied data set, what does that look like? So here we're saying we get around to, we should write down these numbers somewhere. Where do I want to write them down? We'll just write them in temp.text. Or we'll say envim results.text or something. And what do we say here? We're saying that we're kind of happy around iteration, what was that, 600 with a loss of 0.35. Was like hand wavy, almost good enough. So let's just say training on single image looks okay after approximately 600 iterations. And here are some logs. Okay. So now we have that to compare to later. Let's now look at this like places 365 data set. So I was just like browsing through like Torch Vision data sets. They just have a list of these guys, and I just clicked on a bunch of them until I saw something that I thought looked like kind of varied and reasonable, where reasonable isn't very well defined, but give it a sec. So basically just variety of like kind of wide-ish shots, right? Enough that we're seeing like features that we think of like, you know, reasonably high contrast, and hopefully would show hopefully like an image that would look interesting in ASCII art form at the very least. And so let's try training on this, I guess. So we wrote a couple streams ago this like nested directory image loader. Instead of using like the dataset sampler that they gave us, we just wrote our own. The thought being that like we don't really care about like their labels and stuff, and so we don't really want the overhead of doing that. And also like we want to understand what like the code is doing. So we have this like nested directory image loader, which basically like walks a whole directory, finds all the pictures. So we can replace our loader with that. And then here we just have to say somewhere how many images we want to pull out of there. So instead of it just pulling out one, we can say that we want to pull out like 4 or 5 or something, because these images are like significantly smaller than our initial training image. Our initial training image was like 1080p, and these are like 768 by 512. So hand wavy, 4 of them should approximately be the same amount of samples. Which like the number of samples here is like probably an important piece for if we're trying to do like apples to apples comparison. You want like approximately the same number. And in fact, let's actually like print out how many samples that is. So we can say print data.shape just to see. Yes, that's like 6,000, 5,000, 6,000 samples, and I already know that the 1080p image was on the order of like 7,000, 7,500, so good enough. And I guess let's just try training on that and see what happens. We're still going to be validating only on this one image of the, where'd it go? Of that mountain range. Like we're still only validating on this picture. But hopefully it's like a good enough representation that we can see if it's shit or not. We can also keep an eye on the loss. Ooh, training speed is slowed down significantly. That's interesting. So before we were seeing around like 10 iterations per second. This is slowed down significantly. So it'd be kind of nice to know why that is. Who's eating all the time? Because this was not... I did not plan for this. I did not plan for this at all. So... let's think about this. How can we log this? We can log some, like, time. We can add some timers for... we can see if it's taking, like, more from, like, image loading time. So we can say start, or image load start is equal to this. And then we can say sample load start is equal to time monotonic. And here we say return is equal to this. We return the return. And sample load end is equal to time monotonic. And here we can say maybe like image loading took some amount of time. Format sample load start or end minus start. And the labeling took sorry, this one should say labeling. This should say labeling took. And this should say image loading took. And this is sample load start minus image load start. Just to get a feel, who's really destroying us here? Hey, sorry for bothering you. Offer promotion for time. Oops, that's not something that I want to read. Let's ban this guy. There we go. Perfect. Okay, so it looks like we're spending a fair amount of time loading images, but also a fair amount of time labeling, maybe 2-to-1 on labeling. And we can probably reduce label time reasonably significant, like by a lot, by basically trying to batch the labeling process, I'm pretty sure. So let's do this. Instead of labeling here, no, we can't do that. Fuck. Maybe that's a little bit non-trivial. So maybe what we should have done is just left this training in the background. Yo, Happy New Year. Yeah, okay, so here it's like performing... wait, hold on. Why is it performing okay now and it wasn't before, right? So here we're saying like, this is about the speed that we expected training to go at, and it's slow. We saw it being really slow before. Maybe it's because I was using some like memory by having like the visualizer open at the same time. This looks a lot more reasonable. No editor command, but that is NeoVim you're seeing on screen. Okay, so performance here seems fine. I don't know why. I imagine that the extra memory usage of the visualizing script probably didn't help. But we can give this guy maybe like, give him time to get to step 600 and we'll see how he performs. I should have saved the other output over time, but I'm pretty sure that we saw a better performance at around iteration 200 than we're seeing now. But it makes sense because we're no longer testing on the same image we're training with. Yeah, it would be interesting to see. And we're also starting to see that like loss is not going down to the same extent that we saw it going down before, right? When we trained on like only that one single image, we saw us approaching like, I think around like 1.0 at this point. And we definitely saw it approaching, like, what do we see towards the end? We saw results. We saw it like in the realm of like 0.3 was when we were like kind of happy with it. And here we're seeing it's not really like trending downwards anymore. But we'll let it get to like 600 iterations just to see. But I would bet that it's not going to do too well here. Let's give it a sec. Are you normalizing and or augmenting the images? Not yet. Okay, that's not actually too bad. Actually, it's not as good as it was last time, but that's not awful, even though the loss isn't as low. So this is kind of why I think it's important to come up with some sort of like validation metrics, right? Because what we're seeing here is like our loss numbers, which is the only number that we have right now that are like for how good are we. We're seeing that like the numbers are like completely fucking different, like not even fucking close. But maybe the performance is like almost good enough, right? Probably not as good, but like almost good enough. And so the question is like, well, how almost good enough is it? Would be kind of interesting to find out. Yeah, because like that's not too bad. Not too bad. Yeah. Are you so re-normalizing and augmenting? So right now our normalization is just going from we're like taking all of our images and just sticking them into like 0 to 1 range. Certainly there's a better answer than that, right? Because like I know that other neural networks do they basically like try to set the mean of all images to 0 and the standard deviation so that like the majority fall in the range of like 0 to 1, I think is like, or -1 to 1, I think is what they try to do. I can't quite remember. But we haven't tried that yet, but I'm pretty sure that would improve results. But I'm trying to kind of avoid like that type of work until we have a metric, right? Until we have some way of knowing if making changes makes us better or worse. There's no point in just like randomly changing stuff is kind of what I'm thinking. So that's why this is coming like kind of early in the training process. Okay, so what do we want to do? Pretty common in neural network training to basically take your data and segment it in some way so that you have some images that you train on and some that you just only use to check if your training is okay. The idea is that like, say you had like 1,000 images and you come up with like a really, really fucking good neural network, right? It's like fucking killing it. And it's like, it's getting like every single image 100% correct. And then you go out and you try it on something else and it just doesn't fucking work anymore. And you're like, well, why is that? Like, how come my results are like really good and the results on other stuff is like not very good? And generally speaking, there's like this concept of like overfitting, they call it, where basically like if your neural network has like enough memory in it, like if it has a way to store enough state, theoretically it could memorize exactly what you trained on and just remember the answer. And it could be that like however it's remembering to get that answer is not like general to all problems, right? Or even if it's not very smart, but the only things that you showed it were like this exact like a very small subset of like reality or like the world that you're going to show it in usage, it might still not remember. So the idea of like splitting the data sets up is you basically say like, okay, we're going to try to like have some things that we haven't shown you when you're training, see how you perform, and at least hopefully we can combat that like surprise a little bit, right? Because like you probably don't really care about its performance on the things you trained, you care about its performance on everything. So that's the idea. You can still run into problems there, of course, right? Like if you only showed it pictures of a white wall in your training and then you showed it another white wall in your validation, you're still like, well, what happens if you show it anything other than a white wall? You still wouldn't get the answer to that. But the hope is that this like data that we've downloaded is like varied enough that if we just split it randomly, that we'll get enough variety. So let's start there. So presumably we're gonna have, okay, what do we have right now? We have this like image loader, and he like walks this whole directory and pulls out all the images. I should probably write down time here. Sometime before 29:30 is when we start on this. So he walks the whole image folder, and we just have a list of images here. There's a couple things that we might want to like think about here. One is like, we could just randomly split this, right? We could say like, okay, we get our images. We could basically set like, take the indexes of the images, randomize them, and split them in half, or not in half, but by some metrics. The important thing to think about randomizing is because if you just sorted them by path name, I'm pretty sure that these paths might actually have some sort of structure to them. And so if you just split them at like the 90%, you might always show the same pictures later. Hold on, let me see if I can like pull up a file manager and show that. So if we were using like the non-validation set, they basically sort them by like category. And here you're going to say like, oh, here are all the pictures of fire stations. And it's like, okay, so if I were to just like segment my data set by name, which is probably how they're going to be like loaded, then you would only like, your validation set would be entirely Zen Gardens. And it's like, well, that's not like a very fair representation of like the whole world. So what I'm thinking is maybe we randomize these images and split them. Now, you might also think, well, what if we wanted to like compare over different runs? Wouldn't like which images we train on and which images we validate on, couldn't that affect like the metrics? And I think the answer to that is yes. So probably we need some sort of like reproducible way to generate this. So either we like get the same input and make sure that we get the same output, or we like pre-split them by folder. And that seems kind of reasonable to me, right? Splitting by folder, that way you have like a constant thing that doesn't depend on code that you can use in the future to validate, like compare results in the future. So you go back, you make some improvement, you know, a month from now, you might want to go back and look at the same validation data and see, did I improve on that exact same validation data? That might be kind of useful. So let's say that we don't need any code change here, and we'll just pre-split our images. Seems reasonable. You have some software engineering experience before getting into ML, right? At least some. Yeah, actually, I would say that my ML experience is like pretty limited compared to overall software, right? Like I think this is the first time I'm really like trying to make a network from scratch, which I actually don't know if people do that in the field or if it's common to just like start with some paper and modify. But yeah, I've done like 10 years of software, maybe more. If you depending on if you consider like, you know, doing like writing scripts in high school software. But yeah, I've been doing this for a while. ML less so. Okay. Let's think. So we need like a way to like pre-split our images. So we have what we're training on. Fuck. Okay. We have 3,600 images in this folder. We don't really know if they're going to be randomized in any way. And I think that like this is like a data set that I've downloaded that I kind of want to keep as it is. So maybe what makes sense is we'll make a like train folder and a validation folder and basically just symlink into this folder. That seems reasonable to me. Yeah, let's do that. And so probably what we should do is write a script to randomly pull out images and randomly sort them. Okay, yeah, let's do that. So we'll say split train val.py. This is just like a one-off script, so it's not too important. I'm not going to like handle like proper argument parsing or anything. And I'm just going to say source folder is equal to places 365 val. And where are the images? In val large. And we're going to, what? Import from pathlib, import path. And we can basically just say source folder as a path. We're going to, I guess I'll just make this lowercase because it's easier to work with. Even though I usually uppercase globals, in this case it doesn't fucking matter. So source folder, glob, all JPEGs. Because I happen to, well, actually, I don't know this, but I suspect that they're all JPEGs. All right, and so then we can just like print out this real quick and just see what we get. It's easy to tell because you're using words for variable names instead of single letters. Yeah, I guess math people, which I guess like neural, like ML people are come from math more, I think. Math people love single letter variables. I'll never understand that. When I read like algorithms, and I've seen a couple times people like, you know, you read a paper, you copy paste, you don't like copy paste, but you translate that algorithm to code. All of a sudden now you're stuck in this like weird world where it's like, well, do I fucking rename the variables? or do I leave them as they are? Because you kind of want to like leave them the way that they were used in the paper. But then if you try to like make modifications, like you just look at like letter soup. It was just like, you know, you could argue that like you should learn to read letter soup because like words are just letter soup if you think about it. But yeah, I don't know. I don't know why math people don't just like, why don't they like words that are descriptive? I don't know. Do you have a particular use case in mind for this network, such as focusing on particular types of images, etc., like landscapes? I don't really. I've noticed that I don't know if this is set up right now. No, it's not. But like in this file manager I'm using in my terminal, they kind of like show image previews on the right in text. Oh, probably if I have, they're saying no such thing, W3M image display. So something like that would be kind of cool to be able to like show images in the terminal. Maybe like as like an effect that you could put in a video player, right? I don't really like have any idea exactly, but I do know that I want it to be fast and I want it to be portable, right? So I think probably where this project will end up is I do want to like eventually get like some sort of WebAssembly thing version of it where you could like upload a video, like maybe upload a video to a website, process it locally in like JavaScript, WebAssembly, and have it like rapidly come out quick the other side. Maybe like a video game shader effect. I don't know. I haven't really thought it through. But I want it to go fast. It's more about I think the project is much more about the process than it is the final result. There's no real good reason to make this thing at all. There's no reason for it to exist. But it's fun to make. Okay, so this glob of paths did give us a bunch of paths. Wonderful. And so we can then can you just shuffle the list and then split it? Python shuffle list. Is there like a built-in random import shuffle? Sick. Import shuffle. And then we can just shuffle this. None. Okay, so it shuffles in place, I guess. So we'll say JPEGs is equal to a list of the JPEGs. And then we shuffle the JPEGs. And then we print the JPEGs. And now we should see them show up in a different order. Great. And then we can just randomly segment them. So we can say len JPEGs is some number 36500. So we'll say num JPEGs is equal to this. And we'll split them at like, I don't know, 20%, 10%. I guess it depends. Let's see, there's how many of these guys? 36,500. I don't want my validation to take that long. So for now, I'm going to actually split them pretty heavily towards training, I guess, because like for validation, I'm probably going to run over the whole set every time I validate. I don't want too many. So let's just say that we'll take 500 for validation. Num val is equal to 500. And then so we'll just say the training images is JPEGs 5 or num val onwards, and the validation images is everything up there. Easy peasy. And so now we should be able to say that we want in our train folder. Train folder is going to be what? Path train. Easy. Val folder, validation folder is going to be path val. And we'll just make both of those folders like this. And I guess we can just say for image in val images, we're going to just symlink them in there. Fuck it. Blaze it. Val. So we're going to say image dot symlink to make this path a symlink pointing to the target path. Other way. So I want val folder with image path, but only the final part of it. So how do you like pathlib python extract name? Is it just dot name actually? It might be dot name. Yeah, dot name. That looks right. So image name. And we're going to make this a symlink to the image. And we'll do the same for train images. Which doesn't exist. Training images, of course. Of course. Hello, hello, just got here. Can I get a 15-second explanation of what you're working on? 15-second explanation. Overall, turn picture into text. Text look like this, right? Letters from font. And this slow to make, so train neural net to do faster. Approximately. And locally, what we're working on right now is splitting up our training images so that we have some that we can set aside to like benchmark with effectively. Okay, I think that if we just run that split train val thing, wow, that ran hella quick, and we have a train folder, and he has 3,600 images. We have a val folder with 500. These guys symlink, and they symlink incorrectly. Fuck. Okay, so probably we just need to make sure that this symlink, they're probably using, we probably need to make these like absolute paths. So I think there's canonicalize, is like path lib canonicalize path. Basically turn it like from the relative version to, resolve to the absolute. Is that right? Let's see. What was the command? Python 3 split train val. All right. And if we go to val, these are blue now, which probably means that they're correct. And so now, I guess we can just update our training scripts. Probably our training scripts should not have like the training data and validation data paths like hard-coded. So we'll add to our script train path or training data. That seems reasonable. And validation data. And destination for this is going to go to go to training data path, because I don't want to get confused later between like, well, I have like the path to the stuff and the actual stuff. Just appending path to the variable name is like kind of useful there. And dest here is going to be validation data path required equal true. We've done some like bullshit stitching here, so these will automatically get turned into like variables in here. So our image path now turns into training data path and validation data path. Okay. And now we have to, before we were validating on a single image that we were loading up front, so we don't do that anymore. Fuck that. Our sampler for training comes from training data path, and we're going to say this is the training sampler, I guess. And the validation sampler is going to be the same thing. Like this. But from the validation data path. Now, you can argue that since these guys are like passing a lot of arguments and stuff, it's going to be annoying when we inevitably change this. So it's kind of, you could say like make sampler is equal to a lambda path that just does this. And then you can call make sampler with training data path and validation data path. And then during training, we use the training sampler. And during validation, what's kind of weird here is our validation data, or sorry, our sampler right now. Oh, he does have a way to get a specific sample. Sweet. So we can just ask for how many samples there are, which will just return self images len. Nope, not .len. Len bracket bracket. This is Python. Length is a function, not a member function. Which I think this just calls the same thing, I think, as this. So it's like, I don't really understand why Python does it this way. Maybe there's like other options for member variables. What the Python len? I'm getting distracted, but I'm now kind of curious. Difference between len and len. Len is a function to get the length of collection, which by calling the object len method. Special attributes are special and usually more than meets the eye. Should not be called directly. Why? I don't know why they do it this way. It was decided at some point a long time ago that the length of something should be a function, not a method code. Reasoning that len a's meaning would be clear, but a.len would not be clear. That's crazy. This seems like, I guess, like, if you were to read it like a sentence, you'd be like, the length of a is versus like a's length is. They're both the same. I don't really know. It seems like it's fine to say that you want it as like an external function. I like get that. But then saying that external function is implemented, like if you create any class that could have a length on it, you're supposed to then implement this. It just feels weird to me. You might as well have just made this guy the actual function. But okay, whatever. Some old-fashioned design choices that wouldn't have been made today. Okay, you know what? I'll take that. Okay. Or this isn't num samples. This is num images. And so now when we validate, instead of rendering the full image, what are we going to do? What are we going to do? We're probably going to iterate our whole validation sample area. So we're going to say self. What are we going to do? We're going to say for image in, or I guess it's data and labels, in validation sampler. We actually have to go over num images. We're going to say for image number in range of the images. That seems reasonable. We're going to say do something. Do we want to render the image out? Probably rendering the image out doesn't make sense. Especially if it's expensive, right? I think that when we render out the image, that's way more expensive than actually just running the network. Maybe what makes sense is we can like maybe save processing of this data for later. All we really want to do is write down what the answers that we got are. I think that makes sense. Because if we just write down the answer, then if we don't care about the performance until some amount of time in, we can delay processing till that point. And then we can only process the ones we care about. So probably what makes sense is we should write down the images, their sample width, sample height, and we can then figure out what the samples would be from that later, probably, assuming that the sampling code stays the same, which it might not, but that's probably fine. Well, let's think about this. Let's think. What is like the purpose of this? What is the purpose of any of this? You could argue that if we're just going to train and then check performance at the very end, there's no reason to actually do anything here in our validation set. You could just write down the checkpoints and in an external script, load those things, compute the labels, blah, blah, blah. And I think I'm okay with that. I'm okay with keeping it up for now. Usually, like, if you were going to, like, train something and leave it for a while, it might make sense to get those stats as you go so that you can, like, decide when to end it. But I think for our purposes, I think I'd be okay with basically saying, I'm just going to dump some data in here every once in a while. And, like, if you want to decide if you want to be done, run it in a separate script. Run this script to check. That seems more flexible to me in some way. So let's just do nothing. Blaze it. Sure. And then here we don't need the validation sampler. Here we don't need to pass in validation data. Yeah. That seems reasonable to me. So now we train on this like big set of training data, and we dump out our weights, and we like the way to load the model. And then right now we have like this like benchmark script that we're using as a way to like, well, how long does it take to run this guy? But here's all the code that we need to like load a network back and run him. So maybe what we do here is we could, okay, there's two paths here. We have this, like, we have two scripts. We have one that's for, like, benchmarking right now that loads a model and runs it on a image. But we also have one for visualization, which is like what renders out this guy right now. And he's basically says, like, sorry, let's refresh. This script basically says, like, okay, I've got an image. Here are, like, the labels that I would generate. This is, like, the perfect answer. You could argue that we should adjust this script to support running the network as well. And then instead of showing us the perfect labels, we could also show us, like, how our network is doing. But for now, I think I'm going to adjust the benchmarking script. I think that will get us to, like, an answer faster that says, like, if we just wanted to know how well is the network doing. Okay, so we're at 50 minutes now. And let's try to work on making some sort of validation metric. So what's, like, the most simple thing we could do? The most simple thing we could do is we could run over every single image, generate labels for it, run the network, and then just compare the labels to, just compare the labels. And we could just say, how many did we get right? Out of this whole set, how many did we get right? Let's do that. Yeah, let's do that. So in the background, we should probably be training something so that we have something to work with when we finally have the code for checking to be, like, is finished. When it is finally finished. There we go. So this no longer takes in an image path. He just takes in training something. And this is going to come from train, I think. Is that it? Sampler is not defined, so we're going to fix that. Train.py, sampler.glyphcache. This is going to be... Well, I guess we changed it to train sampler earlier. Training sampler. But that's no longer required because we only have one sampler. And I guess this make sampler thing actually isn't required anymore either because we're not going to use the validation data in our training script. So let's do this. There we go. And this guy goes back to normal sampler. Anything else we have to handle in here? Training data path. All right. So I think this will run now. So if we just run train down here. Looks like he's good to go. Looks like he's moving. Looks like he's grooving. And we can just start working on the benchmarking script. So benchmark isn't really the right name for this anymore, but that's okay. And so we're going to, instead of pulling in a single image here, we're going to do the same thing where we construct a image loader. But this guy is going to come from, instead of the image path, we're going to say validation data path. Validation data path. And which means that our argument parser now, instead of taking an image, is going to take in validation data, which goes to validation data path, which is a required variable. And, oops, I switched files by mistake. We need to import this, like, nested dir image loader thing. Great. And now we're going to generate labels and compare. So I guess we go for I in range, sampler, num images. We get the sampler. So we have data labels is this. We then can just render the image. So before we were rendering an image that came in as a full image, but now we've already got it split up into samples. So we can just say here, this is samples. Which seems reasonable to me. I guess if we're going to render out the full image at this point, well, maybe we don't have to render the full image at this point, right? Let's leave this render full image thing as it was. We'll just comment that out. And instead, all we'll do is we will, what? Run the network. run the network on the data. Output is equal to this. And we're not going to even think about rendering the image. We just want to know how many does he fucking get right. So what does he do now? I guess we're going to have to print out the shape of the output and the labels, so I'm not actually sure what they are. So can we run our benchmark? And we're going to run him on validation data is from val. Okay. Model params is coming from... Let's stop this training, and we will back it up so that we don't forget, so we don't accidentally delete it later. We're going to rename this to places 365 trained. There we go. So our model params are going to come from training output, places 365 trained, model params. Our weights are going to come from training output, places 365 trained, and here we have some checkpoints, some that we wrote stuff down. It's running off the screen, so I actually can't tell, but I think 1001 is probably the last one. We don't render out an image anymore, so no output. And is that it? Maybe that's it. It still thinks that we require an output, but we don't. So we're just gonna get rid of that bad boy, because he's not used, because we're not rendering an image anymore. And okay, so he actually doesn't like. I forgot. Okay, so our network. He takes in a one-dimensional array, but this guy comes out as a two-dimensional array because it's a picture, and so we just have to reshape to, well, let's print data shape here. It's probably a 3-dimensional or 4-dimensionals. Let's see. He's got 1,400 samples that are 19 by 12, and so we just need to convert this into 1,400 samples that are that linearized, so we can say data.reshape data shape 0 and then data shape 1 times data shape 2. Arguably, this should be done by the sampler itself, but you could also argue that the sampler doesn't know the neural network architecture, so I think that's true and reasonable. Okay. So now when we run this, we have our data is 1456 by 1525, and our labels are 1426. Oh, sorry, this is our output. So output, we have 1525 answers. So that's probably the number of characters. So probably we either take the max, we probably take the maximum. Certainly. We probably take the maximum of that. So say output.max dim equals 1. Which is probably, we probably have this code here. Predictions, did we take the maximum? Yeah, we took the predictions maximum here. Yes. And we can say that the predicted, and here we can just compare this to the label. Predicted equals labels. Well, here we should probably print the predicted shape, just to make sure that it lines up. So let's see. So he's 1525. Okay, those are the same shape. And we can just say print predicted equals labels. And that should give us trues in the cases where they match, falses otherwise. Cool. So we do see some trues. We see some trues, we see some falses, right? True, true, false, false. So that's a good sign. And then we can probably say, well, what percentage do we get right? So we can say matched is equal to 0 up here. We can say total also equals 0. And for each time, we're going to say matched plus equals predicted equals labels sum. And total is going to plus equal predicted shape 0. Right. So how many things do we predict? How many do we match? And then we'll just say here, since it's like slow, we're going to say predicted or percentage correct is just going to be matched over total times 100. And then we write percent here. That seems reasonable. Let's see if that starts to look like sane in some way. Okay. So 55% correct. That seems like a probably like reasonable answer. And then let's run this on the GPU just to try to like get that to go faster. There we go. And it looks like we're like at around 60% correctness, which is like a great place for us to start from, right? We can also try running this on an earlier checkpoint just to see if it's improving over time, right? If we run it after 200 iterations, the number's way worse, right? We're going up from like 50 to 60. Way worse is kind of a stretch. And let's say that we want to look at where does it start? Say we didn't do any training. We start at the first iteration. After one iteration, we're at 30%. And so we've gone from like 30 to 60% during training. That's not crazy. Yeah. Okay. So we have some benchmark. We have some benchmark. We don't really know if we like what we see. We have no way to check that. But we could assume that if we were to get good labels, that we would be able to check that against what the labels were supposed to be. So our scripts right now support looking at that. So let's try that. So we're gonna look at what val places 65. Like anything. I don't really care. Like I guess we'll just copy paste one. I just want to see like approximately what do those look like. Fine, I'll punch in the full path for you. Just for you, script. That's interesting. He doesn't like this in some way. So there's probably a bug in here with our like resampling code. Let's see, where's this going from? This is going from 266. So expanded size of tensor 37 must match the existing size 36. So I guess we'll just say plus the minimum. Oh, fuck. I don't know, man. What's going on? So the glyph cache thing that we're assigning from is probably the bigger one. Print glyph sampler glyph cache shape. 36. I see. So our sample is like a little too big. So probably our sampling split up is like kind of fucking wrong here, which is annoying. How is that possible? So you're telling me that like output print out output y start output y and minus this. $37. How is that possible? How is that possible? We're going through our number of samples. We're feeding in from the source resolution into our neural network. We are then outputting a like bigger version of that or different size of that because it depends on like the glyph render size. And so we say we have a fixed number of samples. And we are just iterating over those samples. And they're always the same. So this is on the first iteration. Our sample height for comparison isn't matching correctly. I see. So our sample height for comparison is just going to be the glyph cache size. There's no other way about it. Yeah, so this should be sampler glyph cache shape 1 and 2, I think. Okay, there we go. So that's now labeling correctly. And do we like what we see? That's a pretty picture. I don't like this. Not gonna lie. Maybe it's because the characters are too big relative to the picture. Right before we were saying that our pictures are always gonna be 12 pixels wide. But here, maybe what we care more about is like size of the sample relative to size of the picture, right? So say we half this, just theoretically. What happens if we were to make the sample size much, much, much smaller? What do we see here? Refresh, refresh. That looks a lot better if my memory is serving me correct. And I do still kind of like that as a whole. Maybe this is like a bad example also to some extent because it's kind of like bland, I guess. Like contrast is kind of low. It's all kind of dark. So it's like when you look at if I were to like cover up the original picture, I don't think that you would be able to tell what this is. But maybe that's like kind of reasonable just because of like this is just like a blob, right? So maybe let's look through our validation photos and see if there's something more interesting in there. Are any of these more contrasty? This is kind of fun. 1408. 1408. Let's see what we get. Oh, there you go. That's kind of nice. That's kind of cool. Let's try back with the original sample size, 12. Yeah, okay. I think that we certainly are going to have to like reduce our yeah, we're going to have to adjust our training so that the sampling is relative to the size of the picture. Because it just looks way better at like 6 pixels here. Okay, refresh, refresh. Okay, and then let's go back to our benchmark script and at least go back to rendering an image, and we'll just pass in 1 to render just to see. So we're gonna load up. I guess we'll just load up this one manually for now. I just want to kind of see how good it's doing as a whole. So what picture are we running here? Visualize this guy for now. We're just gonna hard code him in here because I'm just trying to get a feel. So we're gonna say image open this, and we know we have to convert it to monochrome, and then we convert this into a NumPy array. Yep. The image gets divided by 255.0 because we want it to be in the range 0 to 1. And we also want it to be a torch tensor on the appropriate device. Then we can pass this into here. And we can just save this to test.png just to see. And let's do all of this before we do any of that other stuff so that it happens quickly. Okay, and so this was with the latest and greatest, and let's just kind of see, does that look at all okay? Refresh, sort by date. Other way to test.png. Okay, so we're pretty far from it being reasonable. Oh, but sorry, that's not true, because this is trained at the bigger resolution. Okay, here's what I'm gonna do. I'm going to adjust my training script to train at the more granular resolution, which right now is just hard-coded, but we'll deal with that later. We're going to start training. Hopefully it works, like nothing crashes, which looks like it is. And I'm going to use this time to go to the washroom because I have to go to the washroom. So I'll be right back. Give me like 2 minutes. And we're back. No checkpoints yet, though. We're almost at a checkpoint, though. They come out every 200, so almost there. Almost there. There we go. And so we see loss 1.5. We should actually have double the number of samples per... Not double. Quadruple the number of samples per iteration now. So I wouldn't be surprised if it actually got a lot better, a lot faster. And hopefully, if we run our like benchmark script now, and we run it on whatever, where we are, training output, whatever we just trained on. Shit. So this is training output, test train model params. Hopefully, we wrote down enough previously to know that this will adjust for the like smaller sample size automatically. We should go to test val, or not val, test train. And there's probably one dictionary to look at here. Nice. And I can't use the GPU for this because the GPU is currently training, but we can run this on the CPU and see what happens. So it looks like accuracy of around like 65%, 60%, which is about what we were seeing before. And does this look... That looks kind of like a plane. I don't think it looks as good. It definitely looks better than like before. Right before we had this like blocky piece of shit. This looks more like... I think that if you were... I don't think that if you gave this to me, I would be able to tell you what it is. But if you give it to me next to the source picture, that's okay. And it's like... It's almost as good as this one, to be honest, the labels. The labels got like the glass around like the hood a little better. And definitely like there's like more contrast around like the wings and stuff. But it's close. Okay. So then the question is, what do we want to do now? Presumably, I guess we want to get closer to correct. So what we should try to do is we should try to see if this number goes up with like a different network architecture, right? Because what we have right now is pretty fucking stupid. What we have right now is where do I draw this? Oh my god, everything's also shit. Oh no, did I Oh, bring me back, please. Oh, are we good? Okay, it's still catching. Whew. I don't know if my stream just got like fucked there for a second, but it looks like my camera's still tracking me okay, and the mouse is still okay. Whew, I hate it when I man. Okay, so at some point we started on this. So this is 01, 14, 04, 5. Somewhere in the past, we started on... This was more like try training and using metric. And now we're going to say we want to actually do some improvements. So let's say now we are going to try improving the model. So we want to see if there's any like things that we can do that will make the model give us bigger number now. And so if we look at our like network, it's pretty fucking stupid right now. We have like our inputs. They are connected to like a layer, like just 15 nodes. And then we take those 15 nodes and we attach them to the output. And so the thought there was that like we originally just had the inputs connected directly to the outputs. That wasn't very good because basically all that allows the output to do is basically say like how bright is each pixel, and I'm going to use that to just decide. Going to use that to decide which character is best. And so we're like, well, we'll put something in the middle, and hopefully 15 things is enough for it to like get a good idea. So this is actually probably going to be a worse performing network because you only get 15 things versus like the 228 pixels you had before. But it also like reduces computational complexity because instead of having to multiply each pixel by each character, you now have to multiply like 15 by each pixel and 15 by each character, which is like O of n plus n instead of O of m times n. But now we're seeing that like it's not generalizing well enough from this, which kind of indicates that like the network capacity might not be big enough. So I'd be curious to see what happens if we just kind of like throw a couple hidden layers in here, and maybe we'll make them like fucking big for now, right? Because we don't actually, we don't. I think that like the network itself is not like a limiting factor here. So we should just be able to say, okay, we're gonna make 5 layers of stuff, and we can just kind of say like, well, maybe these guys will like learn some complex behavior. We don't really know what. But by stacking layers, you're basically allowing it to say like you can threshold on things more. So you can like care about more things, and then in the future layers, you can like threshold on things from the previous layers. Maybe that like creates like abstract concepts in some way. Who knows? So let's just kind of throw that at the wall and see if we at least see some improvement. Fuck, I deleted the last iteration, but we were at like 65%. And that was after 200 iterations, which is kind of, fuck. We want apples to apples comparison. So, and these are taking too long. So I'd be at least interested to try to checkpoint more frequently. So let's go in our training script and say, we'll just do the whole shebang every 50. And we will temporarily undo these changes that we made to our network so that we can have a checkpoint at 50 to compare to. Just because I don't want to be unfairly thinking. Why don't you do convolutional layers? Because we haven't got there yet. Eventually we will. But my initial thought was that one layer would be enough. Like hand wavy, one linear layer. I thought that like the problem was simple enough that would be fine. And I think probably we will try to unlock the concept of convolutional layers soon. But I want to see it. Like my thought is, if it works with linear layers, why would we need to find like some justification to do that, I guess, right? Like I don't think like, well, okay. So if I were in the real world and I was trying to solve a real world problem, right? I would read papers, find something that is similar to my problem, and like start from something that's like similar, right? But in this world, where the goal is to like understand what the fuck is going on, it seems like upgrading from like the stupidest thing, which is linear layer, to like just like starting at something complex, like CNNs or transformers or like whatever. It seems like we have to justify those changes. So I think we start with something stupid and then find some way to prove that it's better. I would imagine that we'll get to convolutional layers and we will say it's faster for the same performance, or better performance for the same speed, or better performance for slower speed. And maybe that's like an okay answer as well. But we need to have the initial data to justify that, I guess. Okay, so we have like 1, 2, 3, 4. I'm gonna give it up to 200, I guess. Just so that we can see. We're still seeing loss go down. I think last time we saw loss kind of cap out at around like 1.5 or something. He was kind of bouncing around like 2.0, 1.5. So it looks like we're probably in the same area. We'll say 1.5 here. Fine. That was after how many iterations? It doesn't actually say, but we'll find out in a second. So what we can do is we can back up this training output. So this test train now gets renamed to places 365, 15 for like the 115 layer. 115 layer, we'll say. And let's just quickly run our benchmark script on this again, just double check. But I assume we're going to see something similar to the like 60% we got before. So weights is this, and params is this guy. And we can run this on the GPU because we're not training at the same time. So we're seeing around like 65%, 66. Ooh, yeah, 65, 66. And so now let's try the network with extra capacity. And we'll just see if it gets better. It's possible that just like randomly stacking layers on here might not give us a better answer, right? There's like real, like, because who knows, right? I don't know what I'm doing. I'm just clicking the buttons. And so we should see if it does better, and hopefully will. On the other hand, you're trying to reinvent a wheel here. I know you should start with a very simple CNN. I guess. So we initially, before we started any of this, we did this like experiment where we tried to train a approximation of sine x with as few nodes as possible, right? Because like part of the idea here is that the theory, the hypothesis is that we should be able to do the same thing that we're doing with like our labeling approach, but faster. And so you like, I guess the thought is, if we don't fully understand what's going on underneath the hood here, we won't be able to know which corners to cut to go faster without losing performance. Hand wavy, right? And so I think it's reasonable to start here at like the simple concepts that we kind of understand, because we tried to train sine x with like 3 nodes, and we predicted what the network would do, right? So we trained with like a hidden layer with 4 nodes in it, and we were like, this will probably approximate with 4 lines, right? 4 linear functions that add up together. And it did exactly what we predicted, which meant that we like understood that well enough. And so I think like we've kind of like unlocked that concept, and so we can kind of try to use it here. But I don't think we've like, until I think that we're going to need to like unlock the concept of CNNs as well, which is like fine. It's like, I don't think that we're like fully reinventing the wheel as much as coming up with our own justifications for the wheel that exists, right? You could say that wheels, like the first guy to come up with the wheel, it's like, why did you do that? It's like, oh, well, it's fucking obvious now we have it. It rolls stuff good. And so you don't have to like reinvent the wheel from scratch. But if you were to try to like start, if you had a square wheel, or like, I don't know how to explain this. It's like, it's good to like be able to rationalize the reasons behind things for yourself, I think. And so I want to get to that concept, if that makes sense. Not clear, I don't think, but hopefully that made some form of sense. So we do see loss still going down farther than 1.5. We're at 1.3 now from checkpoint 201. And so now we should be able to say, if we go into training output test train for this guy, and training output test train for this guy, apples to apples comparison, same number of iterations. Oops. I guess I will stop this guy, and I will run the validation here. And we'll see, did our accuracy improve at all? And the answer is kind of no, which is kind of interesting. I would have thought that adding nodes like that would improve the performance. So the thought process here is that more things would let you remember more cases, and that would help you get better results. But that doesn't seem to be the case. We're still seeing like approximately the same. I was expecting like a pretty big increase. So maybe adding depth isn't really what we need here. But we also added width. We went from 15 to 300. But it's also possible that like we just didn't cap out yet. So maybe I should have let it train for longer. And maybe I should let both train for longer. And so maybe what makes sense here is thinking about some options for like what we think is good. So basically we know we with our current network, we're not going to dump into like CNNs and stuff yet, but let's just say with only linear layers, what are our options? We can increase depth, we can increase width. We could also try doing something, hold on. So say we have like a couple of pixels here, right? Our inputs are like 3 pixels. We'll just say that these are like from like the top left 3 pixels here. 1, 2, 3. We're kind of saying that like each connection here is like multiply. So we'll draw a little X here, right? And then when we get to this node here, this has like an add as well. And so he's going to like multiply all of these guys together, and he's going to add some sort of bias at the end. I kind of get it. So you will not use any dropout momentum, batch momentum, etc. Experiment with linear layers. I think that we will eventually, but we just need to get to the, I think that we should start stupid and get smarter over time is basically it. Okay, so this is like what we have for each node. And so what we've done is we made like 100 of these guys, and then we've kind of like, or 300, I said it was 300 here, and we've kind of like stacked up 300 more, they're doing the same thing, and 300 more, they're doing the same thing. And then here, there's some sort of like activation function, right? So like we say basically threshold, we'll call it, which is like basically like some way, so that all that's doing, these like activation functions, we're using something right now called like RailU, right, where it goes like this. So at 0, it starts like incrementing like it did on its input, but anything under 0 just like floors. And the reason to do that from our like SignX investigation was we kind of figured that, well, if you want to add up this arrow, this line, and this line, you kind of need ways to like say this line stops here and starts here and starts here and starts here. And so that's what these like activations kind of give us. Intuition, there's probably other reasons for them, but that's like our intuition right now. And so then we're saying like, okay, so maybe we have like some sort of transformation that this node is doing, that he has like multipliers and thresholds. So you could imagine, I guess, that like, you could look at like, I want this pixel to be bright, I want this one to be bright, I don't really care about this one, so I'm going to zero it out. So maybe like the first layer gains like some sort of like concept of, this guy could find out like, oh, do I think that the top left of the image is bright? He could figure that out. Maybe he doesn't care, but he could think about that. And then the next one could like maybe might want to learn concepts from like both these guys. So one might say like, I'm bright in the top left. This guy might say I'm like bright in the top right. This guy might say like, oh, I have like high variation in the top left, maybe. And so this guy's gonna be like using like multiple of those concepts together here. And so we could increase like depth this way to say, well, we're going to use higher and higher level concepts that have to be built up over multiple iterations. You could maybe argue that you should alter like width this way to try to just say, well, I can like discover more concepts out of the data. But something that I didn't really understand why in all of like the simple network solutions that we look up, or that, sorry, I shouldn't say that I've like looked at so far, they don't really talk about the fact that like, if these are like mid-level concepts or high-level concepts, I would think that you might still want to use these original inputs down the line, right? If you get to the concept, you get here and you say like, oh, I'm like bright in the corner, or maybe I have like high variance. Maybe over here you say like, there's high variance and good brightness in the corner. Maybe you also want to say, but like, what was this pixel down here? So that's kind of something that I wanted to experiment with as well is maybe like adding like connections like this, which I think I actually have seen in some papers. I've seen like stuff they called like dense networks that have like these further backwards things, as well as res nets where they don't go all the way back all the time, but they do add these things that they call like skip connections, where basically they'll connect like 1 to 3 and 2 to 4 and have like some sort of like ability to reference things a little back. So I think I might want to try experimenting with that. And my gut says that training those different experiments on stream probably isn't worth it. So I think I might just kind of call it at off stream. I'm going to try varying depth, width, and maybe try adding some of these like skips connections as well. I might experiment with that a little bit, and I'll kind of compare longer runs of these guys, and I'll get back to you on the next stream for like kind of performance of each of them. And so maybe what we'll do is I'll try to make sure that I'm gathering any logs that are important, and then we can visualize the differences between those on the next stream. And so I think probably what will be interesting is we'll probably find that just this like one raw number of percentage correct probably won't give us as much as we're interested in. So we might start adding in some like graphs and some visualizations of different images and stuff. And I think we'll call it there and come back to it tomorrow. So thanks for watching, you guys. Oh, sorry, there's a couple comments in here. It might be also worth considering different learning rates. Agreed. This guy's saying look up UNets. Let's see, what is that? UNet. Architecture for semantic segmentation. Oh, I see. So he's going what? Pooling, upconv, conv. So he's going like down to something smaller and deeper and then back up. So the idea, I guess, is that you can do more expensive computations on the bottom. Oh, the skip connect. So you're talking about these like arrows here. Yeah. I see. That's pretty interesting. Conv with residuals, if I'm not mistaken. Nice. Yeah, cool. Okay, so that's cool that it does exist. It's pretty cool. Okay, so I will try some things overnight. We'll see where we get, and we'll come back tomorrow. Thanks for watching, guys. If you liked what you saw, I stream most days around 1 or 2 Pacific time for around 1 or 2 hours. Today we're at an hour and a half. Past couple days we've been closer to 2 hours. If you miss a stream or you want to watch VODs or whatever, there's a YouTube link in the Twitch description. There's a Discord there too and a GitHub link as well. So this project is on GitHub, and I'll probably clean up our current state and get it up there hopefully tonight, maybe tomorrow. And if you're watching on YouTube and you want to say hello, there's a Twitch link in the YouTube description. Other than that, thanks for watching, guys. I'll catch you on the next one. Bye!